Hello everyone, welcome to the course CS22032 Deep Neural Networks. My name is J. Lavanya. I am an assistant professor in Computer Science Engineering Department at Sri Venkateshwara College of Engineering. In this video, we are going to study remaining topics on Unit 1. So in this video, we will study Softmax regression, an extension of logistic regression designed for multi-class classification problem. And also we will going to cover the model evaluation in neural networks. In this, we will learn how to access the performance and effectiveness of our models using various evaluation metrics. Softmax regression. So it is also called as multinomial logistic regression. It is the generalized version of logistic regression or multi-class classification. So that is more than two classes. Instead of predicting a single probability like in binary logistic regression, Softmax predicts a probability distribution over all classes, ensuring the probabilities sum to 1. Example of use: recognizing digits 0 to 1, classifying rice flower types, setosa, versicolor, virginica. So categorizing diseases types, like classifying image categories in computer vision. Binary logistic regression can only predict probabilities for two classes 0 or 1. But in real world problems, we often have k classes. Example, predicting whether an image is cat, dog, horse. We need a model that assigns a probability to each class, which ensures the probabilities sum to 1. Softmax regression does exactly this. It generalizes logistic regression to multi-class classification, giving a valid probability distribution over all possible classes. In softmax regression, the softmax function converts raw scores into probabilities for each class. For k classes, let zk equal to wk transpose of x plus bk. So it will be the raw score logit for class K. The softmax function calculates the probability of class K as probability of y equal to k by x equal to e to the power of zk divided by summation of j equal to 1 to the power of 1 to k e to the power of zk. So each probability is between 0 and 1. The sum of all class probabilities equal to 1. So this ensures that the model outputs a valid probability distribution over all classes, making it suitable for multi-class classification. Suppose the model outputs the raw scores logits for three classes: cat 2.1, dog 1.2, horse 0.5. So first step is applying the softmax formula. So probability of cat equal to e to the power of 2.1 divided by e to the power of 2.1 plus e to the power of 1.2 plus e to the power of 0.5. So similarly for dog and horse, we will write like a dog. For dog, e to the power of 1.2 divided by e to the power of 2.1 plus e to the power of 1.2 plus e to the power of 0.5. For a horse, probability of horse equal to e to the power of 0.5 divided by e to the power of 2.1 plus e to the power of 1.2 plus e to the power of 0.5. So the next step is interpreting the probability. So here the each probability is between 0 and 1. So sum of all probability equal to 1. So next step, step 3 is make the decision, make prediction. So the class within the highest probability becomes the model's predicted class. For k classes, the model structure differs from binary logistic regression. So binary logistic regression, one classifier. Softmax regression, k classifiers, one for each class. Step 1. Compute raw scores for each class. Z1 equal to W1 transpose of X plus B1. Z2 equal to W2 transpose of X plus B2. Up to Zk equal to Wk transpose of X plus Bk. So then all the scores are passed into softmax. So by applying the softmax, all logits are passed into the softmax function, which converts them into probability for each class. Cost function. So why do we need a loss function? To train the weights wk for each class, the model must compass its prediction with the actual loss. So for multi-class classification, we use cross entropy loss. Let yik equal to 1 if simple I belongs to class k, otherwise 0. Let y cap of ik equal to predicted probability for class k. The loss function for a single example is explained here. So this loss which maximizes a probability of the correct class, and it penalizes wrong confident predictions, and convex for binary but not strictly convex for multi-class, still optimizable. Gradient descent update in multi-class logistic regression. So to train the model, weights for each class are updated using gradient descent. Wk equal to Wk minus alpha of dou j by dou Wk. So here j is the cross entropy loss, alpha is the learning rate, and Wk is the weight vector for class k. Interpretation of the derivative. If the predicted probability is greater than true label, the weight is decreased. If the predicted property is less than true label, the weight is increased. Advantages of softmax regression. So probabilities are interpretable. Outputs can be directly read as class probability. Effective for a linear separable multi-class problem, and it is simple to train and fast, computationally efficient. Good baseline model, easy to implement before trying more complex models. Limitations. Cannot handle non-linear decision boundaries, may require future engineering or transformations. Performance drops with highly correlated features. It assumes classes are mutually exclusive, cannot handle overlapping or hierarchical classes. Sensitive to outliers with extreme values can affect probabilities and weights. Softmax regressions is widely used in multi-class classification tasks across various domains, like a digital recognition 0 to 9, example recognizing handwritten digits in postal codes, image classification, categorizing images into multiple classes, text classification such as spam detection or classifying news into sports, politics, etc. And then disease categorization, predicting medical conditions from patient data, recommender systems, predicting categories of items a user may like or dislike, and then sensor fault predictions, classifying types of faults in industrial sensors. So simple working example of softmax regression. Let input x represents a flower futures. So step 1, input futures represent futures of a flower. The model computes logics for the three classes. Z1 equal to minus 1.2, and then Z2 equal to 0.8, Z3 equal to 3.1. So second step is applying the softmax regression. So P1 equal to e to the power of minus 1.2 divided by e to the power of minus 1.2 plus e to the power of 0.8 plus e to the power of 3.1, approximately 0.02. So P2 is approximately 0.12, and then P3 is approximately 0.86. So step 3. Step 3 is a prediction. So the class with the highest probability is chosen as the model's prediction. So here the prediction is class 3. So here is the softmax regression pipeline. First one is collect data. It gathers the input futures x and the class labels of y. And then step 2, convert labels to one hot encoding, which represents each class as a binary vector. Example for three classes, 1 0 0 0 1 0 0 0 1. Like the way it convert the labels to one code encoding. And step 3, initialize weights for each class. Set initial values for wk and biases bk, often small random numbers. Step 4, which compute logics zk equal to wk to the power of transpose x plus bk. Then one logic per class, which represents one logic per class. Step 5, applying softmax. It converts logics into class probabilities. So which means probability of y equal to k by x equal to e to the power of zk divided by summation of I equal to 1 to the power of k e to the power of zj. And then step 6 is computing a cross entropy loss. It measures how well predicted probabilities match actual labels. Step 7, update weights using gradient descent. So wk equal to wk minus alpha of dou j by dou wk. And then in this we will adjust the weights to reduce a loss. So step 8 is evaluate accuracy. So compare the predicted classes to true labels on validation or a test set. Step 9 is a predict using highest probability. For a new input, choose the class with the highest softmax probability. So next topic is softmax regression. In softmax regression, which is also known as a multinomial logistic regression, is a popular classification algorithm used especially in neural networks for handling multi-class classification problems. It is usually implemented as the last layer in a neural network. Its job is to take the raw output scores, often called logits, and convert them into probabilities for each possible class. The softmax function does two important things for us. First, it ensures all probabilities are non-negative, meaning they are 0 or positive. Second, it normalizes these probabilities so that when you add them all up across every class, the total is exactly 1. This way, the output can be interpreted as a proper probability distribution over the classes. Let's look at the softmax function formula. For a given class J, the softmax output is the probability that the input X belongs to class J. This probability is calculated by taking the exponential of the score for class J, which we call Z sub J. Then we divide this by the sum of the exponentials of the scores for all the classes from 1 to k, where k is the total number of classes. This ensures that the probabilities for all classes add up to 1. In summary, the softmax function converts raw scores into normalized probabilities for each class. So we know that softmax regression is a classification method that is used when we have more than two output classes. Here the example is given. If we want to classify an image as a cat, a dog or a rabbit, we can use a softmax regression. It works by giving a probability for each class, and the class with the highest probability is the one the model chooses. So the output layer uses the softmax function, which takes all the class scores and turns them into probabilities that add up to 1. So this makes it easy to compare which class is most likely. Softmax regression is commonly used in deep learning models, especially in the output layer of classical networks. Then the difference between the logistic regression and softmax regression. These are the main techniques in machine learning classifications. Let's start with logistic regression, which is used for binary classification problems. That means it deals with just two output classes like yes or no, or true or false. It uses the sigmoid function to produce a single probability value, helping us to decide between the two options. Example, thinking of like drawing one decision boundary to separate the two classes. Now, softmax regression. So, softmax regression, which handles the multi-class classification. This is for problems with three or more output classes, like choosing between the apples, oranges and bananas. It uses the softmax function, which outputs a probability for each class, allowing us to see how confident the model is about each option. Here we are dealing with multiple decision boundaries, one for each class. In short, we will say like logistic regression is your go-to for binary decision, and softmax regression steps in when the choices go beyond the two. Model evaluation in deep neural networks. So it is the process of measuring how well a machine learning model performs on unseen data. It tells us how accurate, reliable and generalizable the model is. For convolutional neural network, evaluation focuses on how well the model can classify, segment or detect patterns in images. Evaluation methods for CNN. Quantitative metrics, example, accuracy, precision, recall, F1 score, IOU for segmentation. Qualitative visualization, example, feature maps, activation maps, grade cam to see what the model looks at. Robustness test, it's checking the performance under noise, rotation, the occlusion or adversarial inputs. So why model evaluation is important? If even if your model performs well on training data, it can fail on new unseen data due to overfitting and then underfitting or data imbalance. So what is overfitting? Overfitting is the model memorizes training data but cannot generalize. So underfitting is the model is too simple and cannot capture patterns. Data imbalance. So some classes dominate, leading to biased predictions. So bias in training set, which training data may not present real world scenarios. For image classification CNN, we use metrics to measure how well the model predicts classes on unseen data. First one is accuracy. So it measures the overall correctness of predictions. Accuracy equal to correct prediction to the total sample. Second one is precision. It measures how many of the predicted positives are actually correct. Precision equal to true positive divided by true positive plus false positive. High precision, which refers to fewer false positives. Third one is recall sensitivity. It measures how many actual positives are correctly detected. So recall equal to true positive divided by true positive plus false negative. High recall is the fewer false negatives. The next one is F1 score. It combines the precision and recall into a single metric using the harmonic mean. So F1 equal to 2 into precision into recall divided by precision plus recall. So it is useful when the data set is imbalanced, as it balances false positives and false negatives. Fifth one is a confusion matrix. A table showing true positive, true negative, false positive and false negative for each class. It helps identifying focusing classes and understand where the model makes error. Model evaluation in deep neural networks. So the next one is a segmentation metric, CNNs like unit FCN. So dice coefficient which measures the overlap between the predicted mask and ground truth. Dice equal to 2 into A intersection of B divided by modulus of A plus modulus of B. In this the values ranges from 0, no overlap, to 1. It is a perfect overlap. So next one is IOU, intersection over union. The formula is modulus of A intersection B divided by modulus of A union B. It measures the fraction of overlap relative to the union of predicted and true masks. Third one is Hanstroff's distance. So Hanstroff distance, which measures the boundary accuracy between the prediction and ground truth. It is useful for precise boundary evaluation, especially in medical images. Next one is a detection matrix. It is a Foster RCNN YOLO SSD map. So mean map, which means the mean average precision. It measures overall detection performance across all classes. IOU threshold based evaluation. Example, IOU is greater than 0.5 means prediction overlaps ground truth at least 50% by at least 50%. So precision recall curves. which shows a trade-off between precision and recall at different confidence thresholds. CNN rely on loss functions to measure training error and guide weight updates. Different tasks use different losses. First one is classification loss, binary cross entropy, BCE for binary classification. And the next one is categorical cross entropy for multi-class classification. And the next one is a general cross entropy loss, measures difference between predicted and probabilities and true labels. Next one is segmentation losses. So dice loss focuses on overlap between predicted mask and ground truth. So IOU loss, which penalizes poor intersection over union. BCE plus dice or a combo loss, which combines pixel-wise accuracy and overlap for robust segmentation. And next one is detection losses, which in this we will find the localization loss and classification loss. So localization loss, which measures bounding box regression error. Example, smooth L1 loss, gloss loss. Classification loss, which predicts the correct object class entropy. Train validation. So test slip. So common splits are 70 15 15 or 80 10 10. So training set which learn the model parameters, and validation set which tunes hyperparameters, monitor overfitting. Test set which evaluates the final model performance. So next one is a k-fold cross validation. So data set is divided into k subsets. Each subset is used once as validation while others train the model. Rare in CNNs due to high computational cost, useful when data sets are very small. Example, medical imaging. Third one is early stopping. It monitor validation loss during training. Stop training when validation loss stops improving. It prevents overfitting while saving computation. Fourth one is learning curves. Plot training versus validation accuracy and training versus validation loss over epochs. It helps to detect overfitting. Training improves validation stalls or underfitting, both low. To ensure a CNN is reliable and stable under real-world conditions, we perform a robustness test. First one, noise set. Add Gaussian noise, blur or other distortions to input images, which checks if the model's predictions remain consistent and accurate. Second one is augmentation consistency. Applying common transformations like rotation, flipping, scaling, contrast adjustments and scaling and all. So the model should ideally produce the same or similar outputs. Third one is adversarial testing. It is an optional one. Test the model against adversarial attacks like FGSM or PGD. It evaluates vulnerability to small malicious perturbations in input images. When deploying CNN, it is important to measure computational efficiency in addition to accuracy. Key metrics include first one, floating point operation, which measures the total computation cost of a forward pass. Higher flops, more computationally intensive. Second one, inference time. So time taken to process a single image in milliseconds. It is important for real-time applications. Third one, model size. Number of parameters often measured in MB. Smaller models are better for mobile or edge deployment. Then the next topic is model evaluation in deep neural network. Why we need evaluating a model? So first we want to see how well the model works on new data, not just the data it was trained on. This helps us to know if the model is truly useful in real world situation. Second one is evaluation helps us to spot the problems like overfitting or underfitting. Overfitting means the model memorized the training data too well and doesn't do well with new data. Underfitting means the model didn't learn enough and misses the patterns. And finally, we evaluate so we can compare different models or settings. This helps us to choose the best one for the job. In simple, we will say like we test the model on new data and we check for learning problems, and we pick the best model by comparing. Then second one is data splitting. So it is a key step in building a model. We usually split our data into three parts. First one is the training set. This is where the model learns. It studies the patterns and it tries to understand the data. Next one is the validation set. In this tunes the model setting, like adjusting the knobs to get the better results. It also helps us to track how the model is doing while it's learning. Finally, the test set. This is used at the very end to check how well the model performs on new unseen data. It gives us a fair and unbiased score. The next one is the common metrics used in evaluation process. So first one is for classification model, where the goal is to sort things into categories. We can use these classification types: accuracy, precision, recall, F1 score, or OCAUC. uh, in accuracy, which tells us the percentage of predictions that were correct, and in precision, this shows how many of the predicted positives were actually correct. Then in recall, it tells us how many of the actual positives were correctly found, and in F1 score it gives a balance between precision and recall. And then ROCAUC, which measures how well the model can separate classes across different thresholds. Now for regression models, where we predict numbers, we use mean square error and mean absolute error, and also the R square error. Mean square error, this shows how far of the predictions are using squared differences. And mean absolute error shows the average error in prediction using absolute values. Or square score, which tells us how well the model explains the variation in the data. These metrics helps us to understand if the model is doing a good job and where it might need improvement. Then fourth one is monitoring training. When training a model, it's important to keep an eye how it's learning. One way to do is by tracking the training loss and validation loss curves. These curves show how well the model is doing on the data it learns from, and on new data it has not seen it. If the training loss keeps going down but the validation loss starts going up, that's a sign of overfitting. It means the model is memorizing the training data too much and won't work well on new data. To fix this issue, we can use something called early stopping. This means we stop training the model when the validation loss starts to rise. It helps us to keep the model from overlearning and makes sure it stays useful. So remember that, watch the loss curves, stop early if the model starts to overfit, and that's how we monitor the training. We monitor training and keep our models smart and balanced. Then next one is handling the imbalanced data. So it is a common challenge in deep neural network learning. In Sometimes one class in our data has way more example than the others. For example, imagine trying to detect rare diseases. Most people are healthy, so the model sees very few cases of the diseases. If we only look at accuracy, the model might seem great, but just by guessing the majority class. But that's misleading. Instead, we should use better metrics like F1 score, which balances how many correct positives we find and how many we miss. We can also fix the imbalance by using techniques like uh, class weighting, overslapping, like that. So class weighting, which giving more importance to the smaller class during training. Oversampling, which adds more examples of the smaller classes to even things out. So accuracy is not enough. Use small metrics like F1 score, try class weighing or oversampling to help the model learn better.